Uh, Good afternoon, everyone. So, welcome to the first webinar of this week that we are conducting throughout the month of October, celebrating the Cybersecurity Awareness Month. So, we have Dr. Euclides Carlos Pinto Neto today, a postdoctoral research fellow at Canadian Institute for Cybersecurity, and he's going to talk about label flipping mitigation in deep learning based IoT profiling. Let me go through Dr. Neto's profile before I give him the opportunity to conduct his talk. So, Dr. Neto is a computer scientist with an MSc and PhD in artificial intelligence and its applications to safety, critical systems, and security. He has been involved in different AI initiatives involving safety and security in multiple environments, such as aerospace, healthcare, and finance. So today he will be discussing his research work with us, celebrating the month of cybersecurity awareness. Over to you, Neto.
Thank you, Dr. Windhya. Hello, everybody. It's a pleasure to be here today. My name is Euclides Neto. I'm a postdoctoral fellow here at the Canadian Institute of Cybersecurity. And today I'll be talking about label flip and mitigation in deep learning-based IoT profiling. So very timely topic. Let's get started. Okay, so that's the agenda for today. I'll talk a little bit, I'll give a brief introduction of the problem and the whole, the current moment we are like the current problems we have with this particular application, let's say, and also talk a little bit about the profiling itself, the label flipping problem, and then I'll give a bit of a review or a bit of an introduction on deep learning and random forest. And after that, I'll talk about the overlapping label recovery, the OLR in IoT profiling. And finally, I'll talk about the experiments, the next steps, and the conclusion for this particular effort. Okay, so when you think about IoT profiling, like when you think about IoT, Internet of Things, we are talking about a very diverse environment, right? Many devices, many services, very, very useful in so many different environments, but at the same time, such a big problem when you think about like the cybersecurity aspects of that, right? So we have so many vulnerabilities and so many problems to be solved there. In different environments, every single environment would present different issues. And in order to understand the behavior of a particular device in a particular topology, we have this concept of IoT profiling. Basically, we are building a profile in order to understand the network, like the networking behavior of the device and also the operation of the device. So for example, if you have two different devices, two different models or two different types of IoT devices, we would have different profiles, but also if you have a single device deploying two different topologies in two different with two different constraints, right? We will set our constraints. We may have different profiles as well. So basically, profiling is a way of like generalizing or trying to generalize the understanding of the IoT device behavior or operation, and it's very useful in many different situations. So for example, there are so many vulnerabilities that we are not even aware of, and then once you have the profile of that particular device or a group of devices, we can just identify when you have abnormal activities in the network, for example, right? Also, there's a problem with device impersonation. So one particular device can be detected as something else if you have a clear and well-defined profile for that particular device that it's trying to operate as, right? So it's very useful. There are many things to do. And here we have the diagram provided by this organization there, that there's a link. So basically, there's a bit of, a diagram that shows us the meaning of profiling. You have many devices. You can imagine you have like multiple types of devices here in different environments. We collect the network data, the traffic data, and we would have profiling services in different layers. We can also rely on machine learning in order to better understand the underlying patterns there. And then we end up with a classification of that particular device model, device version, or even the category, right? If it's not only the particular brand, but let's say camera as a general topic, right? So there are different ways of facing this. Okay, so there's an important area, important topic actually, which is data poisoning. So when you think about machine learning in general, when you take machine learning courses, we usually train a model and then we evaluate the model later on, right? In different ways, different approaches, but then we always consider, or in many cases, most cases, we consider the trained data is something clean that you can use. Of course, you have to pre-process it, but it's something legitimate. The problem is if the trained data, the data that the model is trained on is compromised, it becomes a huge problem, right? Because you're trying to train a model like to learn something that actually is mislabeled, for example, right? So for example, the example of a classification problem here, we have a sign that should be classified as one particular class, as one particular label, and is being classified as something else, right? Because there are some differences in the image that shouldn't really affect the class, but then based on the attacks on the trained data, it happened, right? So that's just one example. Of course, it can happen in so many different ways with so many different objectives, right? In terms of data poisoning, there are so many different ways that people can attack a trained data. Attackers can attack the trained data, but then there's a particular attack, which is the label flipping. Basically, the labels, the instances in the data set are mislabeled intentionally, or not only intentionally, but also intentionally mislabeled. And then it compromises the performance of the model. And depending on the case, depending on how the labels are manipulated, it can also be an open door for attacks, right? So for example, here, again, a visual example, we have a data set with dogs and cats. We just provide everything to a deep learning model, and then it can classify as such, right, as cat and dog here. But then once you have a data set that is like dogs are classified as cat and cat is classified as dog, and then you just provide this data to the model, then there's a big question mark here, right? We don't really know what it is. I mean, like, of course, we're going to have an output here, but then in terms of performance, we're going to have some problems, right? Naturally. But the question is, what if we change, like, we consider this visual examples here, but what if you think about the operation of an IoT, an IoT network, right? An IoT topology, and then think about possibilities in terms of having this mislabeled characteristics. So for example, if you think about a camera, a speaker, a home automation, and next-gen devices, right? They are very different. They have different profiles and everything. But then someone may mislabel a next-gen device as something like a camera or a sensor in order to be classified as something that is more, let's say, it doesn't really have a lot of processing power in some cases, but actually next-gen devices are supposed to. So this would lead to a lot of problems in terms of the exploiting internal vulnerabilities and doing just general malicious activities, right? So based on this problem there, the goal of this effort basically is to propose the overlapping label recovery, OLR, to mitigate the effects of label flipping attacks in deep learning-based IoT profiling. So we just have this cleaning, or more precisely recovery mechanism, that would allow a given data set to be recovered to a state that is closer to the original version, right? So in order to do that, we use cleaners. We rely on cleaners. More specifically here in those experiments that I'm about to show you, we are using random forests and also considering the randomness and the way it looks at the data and the internal voting mechanism in order to do that, right? So thinking about the random forest, like it's a very useful tool, very useful technique for us here, because basically what we have here is it's a model that takes a look at the data from several different standpoints or several different angles. So we have a big data set that is provided, like the normal data set that is provided to the model. We have internal trees, and then these internal trees, they can have different like splits of the data, different chunks of the data, right? And then these chunks can be overlapping. They can have like the same instances across multiple chunks, but also they can have unique and distinguished instances, right? So based on that, we have like several different trees trained with different data, with different data sets, and the opinion, or more precisely the output of those trees, they can vary, and they will probably vary, right? The in terms of classes, there were probabilities, and then we can end up with a final result that, you know, considers everything we have. So the idea is we have the profiling data set, the let's say dirty or mislabeled data set. We provide it to OLR, and then we come up with, or we end up with this recovered version, which is closer to the original data set. And then we provide everything to a deep learning model in order to understand how well we're doing in terms of the recovery. This process is divided into two steps, basically. First one is we just have the data set, and then we extract samples for this data set, overlapping samples, so you can have repeated instances. And then we provide them with, there's another feature here called sampling factor that's also important. So you just provide the cleaners with this particular sub data set, let's say, and these cleaners are random forest. So from this sub data set, we would also have a split of many sub data sets of the sub data set, right? So we do this for M cleaners. And then once you train all of them with this data, we simply, for every single instance in the data set, we basically ask their opinion, or more precisely, we get their outputs, right? So for each particular instance and for each particular cleaner, we calculate or evaluate the probability of that particular cleaner, that particular instance belonging to a particular class. So this, the sum of these terms here will be 1, right? The result will be resulting in 1. And then at the end of that, we just calculate the average probability of a particular instance belonging to different classes, considering the opinion of all or outputs of all cleaners until cleaner M, right? So once you have the average probabilities for each particular class, then we simply calculate the maximum, the class that presents the highest probability of that particular instance to belong to, right? So basically, we just extract for this particular instance the highest probability, and that's the class we assign this instance to, right? So this new label, this new class, would be the recovered class or recovered label, right? So that's our hypothesis and assumptions, and then we show the results in a minute. But then this is a more like a visual way of taking a look at how the process works, right? So this is actually the pseudocode here. So we have a couple required parameters. So we have the vector containing the cleaners, the length of that, the data set, the sampling factors, and also the number of classes. Then we have a couple for loops here. The first one focuses on training the cleaners and evaluating the probabilities of particular instances to belong to each particular class. And then we also have another a loop here to calculate the average probabilities in order to understand for each particular instance what's the highest, what the highest, well, at least we're going to have a vector, right? So we're going to have a vector of all the values, and actually the calculation of the highest, or the argmax, would be down here. So here we would calculate, we actually calculate the highest value in this particular vector, and then end up with this recovered label, right? Okay, so once you do all of this, we just provide the results, the outputs, the recovered data sets to a deep learning model. So there are other models that have a really good performance in this particular problem, but in our experiments, deep learning has, you know, even shallow networks, they're presenting interesting results. So that's the model we're using here. And in terms of the evaluation, in terms of understanding how, like, the improvements of our proposal, we are relying on this particular evaluation method here. So basically what we're doing is we are integrating over different poisonous percentage, like the percentage of labels flipped, right? So in that particular range, we would try to understand how well we are doing in terms of the recovery from the perspective of the metrics, right? So we consider different metrics, so we can just have multiple metrics in this problem. We are just considering the performance of the system with OLR enabled training. Basically, we are recovering the labels and training, and then also comparing it to the performance of a poison training or a training with no recovery procedure at all, right? And then, yeah, so basically what we have here is we are averaging it, but basically what we have here is a simplification of the model. Actually, that's the core, of the model, because in order to better understand the results, what we do at the end of the day is we have a normalization, a simple min-max, in order to understand the performance of this particular model in comparison to what we have as a baseline model, right? So, but that's the core of the evaluation method we are considering. And in terms of the experiments themselves, like basically what we are considering is, first of all, the first stream of experiments, we have the data set, the clean data set. We just load it, we just prepare the data for the model, use the model, evaluate it, have different results, and then we have, and just we can report the results. After that, we have another experiment or another stream of experiments, considering the same approach, however, executing label flipping attacks against our data set. So then we end up with a compromised IoT profiling data set, and then we train to see how well the model will be doing. And finally, we do the same with OLR. So basically, we are recovering the features, the labels, trying to end up with a better version of the data set, closer to the original data set, right? In terms of the data set, we are using the CIC IoT 2022. So basically, this data set, it's all about IoT profiling. It has been, basically, we have a topology of several devices in the IoT lab of the Canadian Institute for Cybersecurity. So there are several devices and like supporting devices like routers, switches, and so on. So there are many experiments in terms of understanding the behavior of the device, if the device is idle, if you are interacting with them, and so on. And yeah, and there are so many different classes there. The data set's available on our website alongside many other devices, many other data sets. But then it's really interesting to at least take a look at the data set to understand how it looks and how useful it can be, right? It can be used in so many different applications. So it's worth it. So in terms of the results, this is the result for accuracy. I'm about to show you more results, but then just to go over all the details here. So here we have the results for accuracy. We have 15 cleaners. In this chart, we have the accuracy and also the label flipping factor, or the level poisonous that we're going to have there. The golden or yellow line refers to the original label. So here there's no attacks at all. Everything is just, the classification is really high performance. The red line represents the label flipped. So as you flip the labels, we just see the decrease in performance overall. And the greenish, bluish line here, we have the label recovery, the results with the labels recovered, right, with our procedure. So we see that as we move forward and we increase the label flipping factor, we still can hold the line. We can improve the performance overall, right? Of course, here we're talking about accuracy, but then when you reach like 0.6, then it becomes very difficult to keep a good result, right? Because most of the data set is compromised. So yeah, but then we can still hold it in terms of the performance. Moving on and showing you the results for more metrics and so on. Here you have the results for sampling factor 0.15. So you see that for accuracy, recall, precision, F1 score, and different number of cleaners, we have kind of similar result, right? We can kind of improve the performance of the labels flipped approach. So of course, you are far from the standard because you have like a perfect data set there, but then we can still improve the overall performance. Same applies to 0.25. Remembering that this sampling factor refers to the size of the data set you're going to be using for training our cleaners, right? So here we increase this sampling factor a little bit. Results, I mean, when you take a look at it, they seem to be very similar, right? And same with 0.35. But then if you consider a different angle of this evaluation, and when you have sampling factor 0.15, and like these are the results for different cleaners, right? Different number of cleaners, actually. So we see that increasing the number of cleaners would overall give us a better result, right? Even though it's very similar, very, very close, right? But that's would improve the result overall. And then in terms of the labels that were recovered, we would have more labels correctly, instances with correct labels or correctly classified, let's say, with when you increase the number of cleaners, right? When you increase the sampling factor, there's a bit of a difference here. I mean, like we see like the lines are very much more closer to like they're very, the difference is not as significant as before, right? So we see that still 15 cleaners seems to be better overall, but then we see that they are closer, right? Same here, we see the distance is reduced. And finally, when you think about the 0.35 sampling factor, then they are very close, right? That's pretty much what we see in terms of the results. Yeah, and in terms of the recovery as well. Okay, so the bottom line is we have like different parameters, different configurations, and for this particular evaluation model, and we see that for 0.15 in terms of sampling factor, we can we achieve the best results. Right? So reducing the sampling factor would lead to a better recovery, while we see also that increasing the number of cleaners for that particular choice is the best outcome, right? So we have an overall improvement of 10% in terms of the metrics. But then when you take a look at the 0.35 sampling factor, we see that reducing the number of cleaners would actually improve the performance, right? So that's a very interesting aspect of this results. And well, it makes sense, right? It makes sense. If you have a data set with like with flipped labels, reducing the number of the sample, the number of instances in the sample would mean reducing the number of, hopefully reduce the number of flipped labels in that particular sample, right? So the underlying distribution, the underlying patterns would be kind of easier to understand while we remove those flipped labels, right? So that's what we're seeing in this chart, basically. Okay, so thinking about the next steps, the first direction they're considering at the moment is label recovery strategies. So we are considering this model. We are based on different multiple metrics that are very relevant for us, but it's very important to consider like different ideas, right? And one of them is interpretability. We've been talking about like interpretability and explainability for machine learning models and how they can help us in order to like better understand the decisions the model make. But then how can we use those outcomes in order to explain what to extract these explanations and improve the recovery procedure based on those particular, let's say, like processes, right? I mean, like not using the metrics or the weights, the configuration of the network, but also the rationale behind it. That's one thing. The second thing is representations. So how can representations help us in this environment? How can we use the representation of a neural network, for example, in order to understand if a particular label is like a particular instance is misclassified or not, right? Second, we have data poisoning challenges. So there are many ways of dealing with data poisoning and many different attacks also. But then once you have two instances in very different spots in the any dimensional space, and then they have different labels, very different labels, like clearly different, it's kind of easier to understand, like to see the differences, right? Because the instances are very different. But then when they are in the intersection of the particular environment that you have in the n-dimensional space, it can become challenging, right? It can become very challenging. So we are also investigating how to improve to making those attacks more challenging and trying to understand how difficult it would be for a model to recover those particular labels in that particular area. And finally, new constraints in IoT, in IoT environment. So for example, we have smart city applications, smart cities, you have smart healthcare, Internet of Vehicles, IOV, you have deployments in ports, we have airports and so on, right? Once you think about an IoT device operating in a particular environment or in a particular company or organization, we would have different characteristics of that particular operation, right? And then this data poisoning attacks, they can focus on the particular vulnerabilities or the particular characteristics of a particular environment in order to exploit possible vulnerabilities, right? Existing vulnerabilities. So that's something that needs a lot of consideration for that particular deployment, the particular topology, but also something that we are considering at the moment. Okay, so today we had this talk regarding IoT profiling in general. We have presented the OLR, the recovery profiling data, and mitigation of trying to mitigate the label flipping problems, right? We have several future directions. So they include federated experiments, they include the different profiling granularity. We are talking about different levels of trying to identify a device. So, and also profiles that can be or categories that can be customized by the user or the company who's operating the devices, right? And this is just a couple points here, right? There are so many other things to test, to try, and also so many directions that you can consider in order to improve the recovery outcomes of our models, right? So thank you very much for your attention. And so if you have any questions, I'm more than happy to take them. So back to you, Dr. Windhya.
Thank you very much, Neto, for that interesting and timely topic. I have a small question for you. Uh, what do you think about applying this recovery method in other IoT applications?
Yeah, that's a very good question. So we have many possible ways of using this particular model or idea in different problems, right? So for example, here talking about IoT profiling. When you think about attacks, for example, like if you have, for example, if you consider the Canadian Institute for Cybersecurity, the CIC IoT 2023 dataset, that's going to be basically IoT, considering an IoT environment, but then considering attacks like DDoS, DOS, recon, and so on. When you think the differences in terms of labeling that particular data, the underlying procedure will be similar, but then the results can be very different, right? So here you are considering the environment of IoT profiling, which has a very specific characteristic in terms of networking and operation overall. But then when you go to attacks, it can be like very different, right? It can be very positive, a positive difference, but it also may require some, let's say, different methods to work with. And by doing that, we can hopefully get the results similar to what we're getting here with the profiling. But that's a very, very good question.
Yeah, so thank you very much, Neto, for enlightening us about IoT and its application, especially in cybersecurity domain. And we will have our next webinar for the Cybersecurity Awareness Month tomorrow at the same time, that is 12 p.m. So until then, stay safe and see you tomorrow.
Thank you, Dr. Windhya. See you tomorrow. Thank you, everybody.
Bye.